launch was supposed to take place late on December 6th, but there were technical delays and countdown holds and hours passed. But eventually, early in the morning, on December 7th, the last Apollo mission to the moon was ready to go. At the time, my brother worked for NASA, and so our whole family was there to see it. I was 12 years old. The video that follows is from NASA. The audio is our own family recording.
1 minute and counting now in the final minute of the countdown. At T-minus 45 seconds, Gene Stern will make the final guidance alignment. This is the launch. T-minus 5:45, and Gene Stern made that final guidance alignment. That's the last action taken by the crew for the space vehicle. Now approaching the half-minute mark. T-minus 33. T-minus 30 seconds, and continuing on now. Continuing on at the second mark, T-minus 25. We'll get a final guidance release at the T-minus 17 second mark. T-minus 17, final guidance release. We're expecting the ignition at 8.9 seconds. 10, 9, 8, 7, ignition sequence.
We were with the other NASA families on a landfill about 3 miles away from the launch. It took 15 seconds for the sound to reach us, but when it did, it was overwhelming. It was the end of Project Apollo, but it was not the end of human spaceflight. This is a graph of the number of human beings launched into space year by year up to the middle of 2014. And this is the end of Project Apollo. So you can see that the vast majority of the number of people that have crossed the Kármán line have done so after that time. Human spaceflight, since the end of Project Apollo, has been, in some sense, most of the story of human spaceflight. It is true that we haven't been back to the moon. We haven't sent human beings on to Mars or beyond. But for the last 50 years, we've been learning a lot. We've been learning how to fly into space more economically. And we've been learning how to live and work in space for months and years at a time. The last 40 or 50 years has been the era of the space station. We've already mentioned the Skylab project of the United States, an Apollo technology-derived project which used a Saturn V to put a large space habitat into orbit. And it was crewed by 3 different crews in 1973 and 1974, the last crew staying for almost 3 months. And they observed the Earth, they studied the space environment, and they learned how to live and operate in space. Meanwhile, the Soviet Union was establishing an ambitious and long-term program of its own. beginning with the Salyut space stations. In the 1970s, the first generation of Salyut had 4 different habitats, supporting a total of 6 cosmonaut crews. The more advanced second generation of Salyut in the late 70s and 1980s had 2 successive habitats, supporting a total of 26 crews of cosmonauts. Salyut was followed on by Mir from 1986 to 2001. Mir was a large, multi-module, long-duration habitat. It was built not in a single launch, but by putting together pieces launched many times separately, and cosmonauts could stay aboard Mir for up to a year at a time. Eventually, Mir hosted astronauts from many countries, including the United States. The space shuttle docked with Mir 4 times. But Mir was plagued with many problems. Over its more than a decade of life, Mir was plagued by equipment failures, power losses, and system failures. In February of 1997, a serious fire broke out on board. The flames were such that the crew had its access blocked to one of the 2 emergency evacuation spacecraft, and only one person could fit into the module to fight the fire at a time. Nevertheless, the fire was soon extinguished. Then, later that same year, there was a collision between the Mir and one of its unmanned Progress cargo spacecraft, and this actually caused an atmosphere leak to one of the modules. The module had to be disconnected, the door sealed off, and never reopened again. And as if all this is not hair-raising enough, at one point the cosmonauts removed a seldom opened panel and found behind it among the electronics a huge gob of bacteria-laden water the size of a grapefruit that had accumulated there. They found bacteria and mold and fungus on surfaces and gaskets and wire insulation. So there were some quite serious environmental concerns about the Mir space habitat. But the purpose of such a program is to learn how to do it, to figure out what the problems are with long-term spaceflight, to figure out how to solve the problems. And by that measure, the Mir program was a rousing success, and it laid the groundwork for the most amazing and impressive space station project of them all. The International Space Station is a vast orbiting complex, over 100 meters from end to end. It's built out of dozens of individual modules and components launched and assembled in orbit, contributed by the United States, Russia, the European Space Agency, Japan, and Canada. And the first components were launched in 1998, and the International Space Station has been continuously operated, carrying a crew since November of 2000. That means for every day so far in the 21st century, human beings have been in space. So we've been learning to live and work in space. But that leaves the problem of how to get there. Human spaceflight in the era since Apollo has been dominated by 2 human-carrying space transportation systems. The first is the Russian Soyuz. The first Soyuz spacecraft flew in 1967. But of course, that was a disaster because the single occupant was killed upon reentry. And indeed, the first generation Soyuz spacecraft lost another crew in 1971, returning from the Salyut 1 mission. So, over the years, the basic design has undergone several major changes. The second generation of the Soyuz spacecraft from the middle 1970s carried two cosmonauts in lightweight spacesuits. This was the kind of Soyuz that participated in the Apollo-Soyuz test project. The third generation Soyuz applied lessons learned during that mission, and it could again carry a crew of 3 and service the Salyut and Mir spacecraft. And finally, the current generation of Soyuz is the fourth generation Soyuz, and it's used as a crew transport to and from Mir and the International Space Station.
So we have separation flag.
And physical separation and undocking confirmed. 11:14 p.m. Central Time, 12:14 a.m. Eastern Time, with the station flying 255 statute miles over the southern part of Mongolia.
The steady success, and since 1971, the impressive safety record of the Soyuz spacecraft is a great exemplar of an approach to the technological problem that's been characteristic of the Russian and Soviet space programs from the very beginning. Find a technological solution to your problem that works well enough, and then stick with it. In the case of the Soyuz, they've been flying basically the same design with some substantial and important improvements for half a century. But that has enabled them to maintain a pretty steady launch rate. They've been flying several Soyuz missions a year for decades. The American approach to the space access problem has been quite different. The American strategy to put human beings in space in the era after Apollo has been based on the ambitious and incredibly impressive Space Shuttle program, technically known as the Space Transportation System. In 1969, as astronauts were reaching the moon, NASA was beginning to think about how manned spaceflight would continue after Apollo, and they began to dream big. They decided to build a system that could solve 3 problems at once. The system would be capable of transporting crew and cargo into orbit, it would be fully reusable, and it would be economical to operate. Of course, as one wag said, of these 3 goals, you can pick any 2. The idea was to build a spacecraft that could launch vertically like a rocket, but then the orbiter part would return to Earth as a hypersonic glider, a successor to the X-15 and the X-20. Unfortunately, budgetary constraints in the 1970s forced NASA to make many design compromises in their space shuttle program. And here is the configuration that they eventually settled on. It's built around an enormous tank of fuel, liquid hydrogen and liquid oxygen, that is disposable once the spacecraft nears orbit. There are 2 strap-on solid rocket boosters based on ballistic missile technology, and then there's the orbiter vehicle, which is about the size of an MD-80 airliner. And there are a number of things to note here. First of all, this is the first human spacecraft to use solid fuel rocket boosters. And the second thing is, notice that the crew carrying spacecraft, the orbiter vehicle, is not on top, but is down on the side of the spacecraft. In other words, the human occupants are a lot closer to the part that shoots out fire. This would have an extremely significant role to play in the history of the space shuttle. NASA engineers had to meet a great many technical challenges to make the space shuttle work. One was simply engine performance. The space shuttle main engine on the orbiter had a vacuum-specific impulse of 452 seconds, among the highest ever flown. They were fantastically efficient engines. Another challenge was the thermal protection system, the heat shield for re-entry. And previous spacecraft had used ablative heat shields. Basically, the heat shield protected from the immense heat of re-entry by melting away. Well, that was not reusable, so they had to have a non-ablative heat shield for re-entry, composed of thousands of very specialized insulating tiles. And finally, because the space shuttle was aimed to carry crew and cargo, it had to be pretty big. It had to support up to 8 crew for more than a week, and its cargo bay was 18 meters long and almost 5 meters wide, big enough to fit a bus. Despite the challenges, the space shuttle worked beautifully. Here's a video of the launch of the Space Shuttle Endeavour. The main engines fire, and once they're up to full thrust, the solid rocket boosters are ignited, and the space shuttle takes off. The entire space shuttle composite vehicle is about 3/4 as massive as the Saturn V, and it makes a lot of noise. The solid rocket boosters are only with the shuttle for the first couple of minutes of flight. Once they've exhausted their APCP propellant, they are detached, and the space shuttle proceeds on with only the main engines, supplied by the giant external fuel tank. Finally, as the shuttle nears orbit, the external tank is exhausted, and so it's detached and drops away, and the orbiter proceeds on to orbit on its own. The U.S. ultimately built 5 space shuttles, each one costing about as much as a nuclear aircraft carrier. Columbia, the first, was launched in 1981 and flew until it was destroyed during re-entry in 2003. Challenger first flew in 1983 and was destroyed during launch in 1986. Discovery, launched in 1984, was finally retired in 2011, as was Atlantis, which was launched in 1985. Finally, Endeavour, which was built to replace Challenger, was launched in 1992 and retired in 2011. The shuttle program lasted 30 years. During that time, the shuttles flew 135 times, carrying most of 1,000 people into Earth orbit. The history of the shuttle program has many highlights, including the launch of the Hubble Space Telescope in 1990, but the key accomplishment of the shuttle program was the construction of the International Space Station, which was essentially completed by the time the shuttles retired in 2011. But that history was also marked by 2 of the worst space disasters ever. Let's talk about those. The first was the Challenger explosion in January of 1986. The problem was the cold weather. It was well below freezing in Florida, and they had never launched a shuttle at such a low temperature. Now, the solid rocket boosters, the SRBs, were constructed in segments, and between each segment was a thick O-ring of a rubber-like material. This material got stiff in the cold, and it cracked. A jet of hot gas from the solid rocket fuel hit the side of the big external fuel tank. It exploded. The orbiter and all 7 crew members were lost. The program was put on hold for 2 years for a safety reassessment, and the shuttle Endeavour was built to replace the Challenger. The second disaster was the loss of the Columbia in 2003. Here's what happened. Ice would often form on the outside of the external tank before launch. It had liquid hydrogen and liquid oxygen in it, so it was pretty cold. Now, this came off during takeoff, but it usually did not do any harm. This time, though, a big chunk damaged the thermal protection system near the leading edge of a wing. The Columbia astronauts had no way to see this and no way to fix this. When they re-entered the atmosphere several days later, the intense heat burned through and destroyed the orbiter completely. All 7 crew members died. And again, the program was suspended for a couple of years for a thorough safety review. But by this time, it was no longer possible to build a replacement for the lost shuttle. The 2 disasters did not have the same cause, but they revealed the same fundamental problem in the space shuttle design. The orbiter, where the people were, was not up on top of the rocket, it was on the side. So when the fuel tank exploded on Challenger, the orbiter had no hope of flying free and escaping. And when chunks of ice fell off of the Columbia fuel tank, they could strike and damage the orbiter heat shield. That awkward configuration, solid rocket boosters, great big fuel tank, orbiter on the side, was a direct consequence of the design decisions made in the early 1970s. NASA would only be allowed to build 1 spacecraft, and that 1 spacecraft would have to do everything, crew and cargo. It would have to push technology to the limits, and budget constraints would force design compromises everywhere. Here's that graph of human spaceflight year by year. You can see the huge reduction in space operations for each disaster. The blue bars representing U.S. launches disappear for a year or 2. The International Space Station is supported entirely by the Russian Soyuz. The shuttle program was ended in 2011. There is not at present a U.S. vehicle to carry humans into orbit. All travel to and from the ISS is done aboard a Soyuz. If we brought that graph of spaceflight up to date, there would be a row of several more red rectangles to the right. But that is about to change. First, we need to note that there are other spacecraft flying. The Chinese Shenzhou spacecraft, similar in design to the Soyuz, has flown several missions since 2003, most recently to the small Tiangong space habitat. And in the US, a competition called the Ansari X Prize was held to privately build craft to carry people into space, not into orbit, but beyond the Kármán line. It was won by a company called Scaled Composites with their craft Spaceship One. It was launched from an airplane like the X-15. Its successor, Spaceship Two, may soon start taking passengers into space. The suborbital flights would be like Alan Shepard's first flight in Mercury, but the passengers would get to experience several minutes of zero gravity, and the view out the large windows will be spectacular. The U.S., meanwhile, has adopted a multi-pronged strategy. It will no longer keep all of its eggs in one basket. NASA is building an advanced spacecraft called Orion and a big rocket to carry it. The project is well behind schedule and a lot over budget, but if and when it flies, it will be pretty cool. At the same time, they have contracted two private companies, Boeing and SpaceX, to develop two new spacecraft to carry people to and from the ISS. As of the moment I'm saying this, both spacecraft have been built. Both have flown test flights without passengers and are nearly ready to go. The Boeing Starliner will probably launch within a few months later this year. The SpaceX Dragon 2 will probably launch in a few weeks. So this is a tremendously exciting moment in human spaceflight. Big changes are coming soon, and huge opportunities are opening up. But that is the future, and so it properly is part of our next lecture. I'll see you then.